Most of the time, the internet does not feel like a thing at all. It feels instant, weightless. A message crosses an ocean in the time it takes to blink. A payment clears. A film begins to stream. A file appears in a cloud folder from a country you may never visit. The whole system is so familiar that it can seem almost immaterial, as if our digital lives are suspended in the air around us. But the internet is not in the air. Not really. It is anchored to shore. Beneath the surface of the world's oceans lies a network of fiber-optic submarine cables, stretching in long, deliberate lines between continents and coastal landing points. These cables carry about 99% of international internet traffic. In other words, nearly every email sent overseas, every international transfer, every video call with someone far away, and every piece of data that moves between countries depends on a physical system most people never see and rarely think about. That is the first surprise. The cloud has a coastline. It helps to imagine what that means in practice. The digital services we treat as borderless are constantly being handed off from one physical layer to another. A request leaves a laptop or phone, travels through local networks, reaches a carrier, passes into a terrestrial backhaul system, and then arrives at a landing station, a place that may look like an ordinary secure utility building on a quiet stretch of coast. From there, the traffic enters the undersea cable itself, crossing the ocean floor before resurfacing at another landing station and continuing inland through another terrestrial network. The illusion of seamlessness depends on this chain of very specific places. And that chain matters because it is not infinitely flexible. The internet is resilient, but it is not abstract. It has bottlenecks. It has choke points. It has routes that carry enormous volumes of traffic because geography, cost, and history have made them the best available paths. When one cable is cut or develops a fault, the system does not simply collapse. Much of the time, traffic is rerouted, but rerouting is not the same as invulnerability. A break can add latency, reduce capacity, and create strain on the remaining routes. In regions with fewer alternate paths, the impact can be far more severe. The lesson is simple. Redundancy helps, but the network is still built from real corridors under real water. That reality becomes easier to see when you zoom out. As of 2024, more than 500 active and planned submarine telecom cable systems were estimated to span the globe, adding up to more than 7 million kilometers of cable. Yet even that vastness can be misleading. The system is not evenly spread along every shoreline. It concentrates through landing stations, and those landing stations are not infinite in number. They are fixed, strategic points where the ocean network meets the land network, where long-haul subsea capacity hands off to the fiber and routers that carry data deeper into cities and countries. Telegeography's 2026 map counts 893 landing stations worldwide, a reminder that this supposedly borderless medium is stitched together through specific places. That concentration is part of what makes submarine cables so important and so vulnerable. They are essential infrastructure for commerce, government communications, cloud services, markets, research, and everyday life. They are also exposed to accidents, natural hazards, and human activity. Faults happen often enough to be part of normal operations. International organizations have cited roughly 150 to 200 global faults each year, and in 2023 more than 200 repairs were reported. Most of those incidents do not make headlines. The internet keeps moving, often by taking another route. But each fault is a reminder that the digital world is not floating free of the physical one. It is built on it. That may be why submarine cables have become more than a telecom concern. They are strategic infrastructure. They shape which regions connect efficiently to the rest of the world. They influence how quickly data can move, where companies place services, how countries secure critical communications, and how much redundancy a region can afford. In 2024, the International Telecommunication Union and the International Cable Protection Committee launched an international advisory body for submarine cable resilience, a sign that governments and industry now understand these systems not as obscure engineering projects, but as a matter of global stability. Still, the most remarkable thing about these cables is how invisible they remain. They do not announce themselves the way satellites do. They do not glow on a screen. They are not part of the language people use when they talk about the internet. We speak about networks, platforms, apps, and clouds as if information simply appears and disappears through software alone. Yet every one of those experiences depends on a hidden maritime logistics chain, a set of lines on a map that matter far more than their public image suggests. That is the paradox at the center of the story. The internet feels like the most modern thing ever built, instantaneous, immaterial, everywhere at once. But its most important links are old-fashioned in the deepest sense, physical, costly, engineered, and vulnerable to the geography of the planet. So the question is not whether the internet lives in the sea. It does. The real question is how we got here, how a technology that began as a way to make distant places feel closer ended up depending on a network laid across the abyss, and how the first attempts to cross water with signals became the foundation of the world we inhabit today. Before there was a global internet, before there were phone calls that crossed oceans in a fraction of a second, there was a far older dream: to make distance stop mattering. In the 19th century, if a government in Europe needed to reach North America, it could not simply send a message and expect an answer. It had to trust a ship, a weather window, a route across a dangerous sea, and a delay measured not in minutes, but in days or weeks. The ambition behind the first submarine telegraph cables was simple and audacious at the same time. Instead of carrying words across water by sail, engineers would carry signals beneath it. That idea changed the rhythm of the world. The first experiments were fragile, improvised, and often short-lived, but they proved something profound. The ocean was no longer an absolute barrier to communication. Once a cable could be laid on the seabed and made to work, even imperfectly, time itself began to shrink. Messages that once moved at the speed of a ship could move at the speed of electricity. Diplomats could learn of crises sooner, merchants could react faster, news could cross an ocean while it was still news. The early years were full of setbacks because the sea was a brutal testing ground for a new technology. Cables broke, insulation failed. Engineers discovered that distance underwater was not the same as distance on land. Pressure, corrosion, weather, and the simple difficulty of building reliable equipment all stood between invention and usefulness. But each failure taught something. Each generation of cable makers refined the design, improved the materials, and learned how to survive a harsher environment. The important thing was not that the first cables were perfect. It was that the basic idea endured long enough to be improved. What makes this history so remarkable is that the purpose never really changed, even as the technology did. The telegraph cable became the telephone cable. The telephone cable became the fiber-optic cable. The language of the network changed, the speeds became unimaginable, and the engineering grew vastly more sophisticated. But the strategic problem remained the same. How do you connect distant places across the sea as reliably and as quickly as possible? Every era answered that question with the tools it had. When submarine cables began carrying voice instead of just telegraph pulses, the ocean grew smaller in a new way. A conversation no longer had to be translated into dots and dashes. It could be heard. That mattered because voice changed the character of international communication. It was not only faster than the old system, it was more immediate, more flexible, more human. Businesses could negotiate in real time. News organizations could coordinate across continents. States could speak to states without waiting for paper to move. The cable was no longer just a line for messages. It was becoming a channel for the daily workings of modern life. Then came fiber optics, and with them a transformation so large it can be hard to appreciate in retrospect. Light replaced electrical pulses. Capacity exploded. The same ocean floor that once carried a few fragile messages at a time could now support broadband systems capable of moving enormous volumes of data. This was not a rejection of the old submarine cable idea. It was its fulfillment. The principle invented in the telegraph era lay a durable line across the seabed. Protect it, power it, maintain it, and use it to collapse distance. Survived every technological revolution that followed. That continuity matters because it reveals what submarine cables really are. They are not an accidental relic from the past, kept alive only by inertia. They are an industrial inheritance. The world did not suddenly discover that undersea connections were useful when the internet arrived. The internet simply inherited a network form that had already proven its value for more than a century. The same logic that once linked empires and trading houses now links cloud regions, financial markets, data centers, and billions of ordinary users. The medium changed from telegraph wire to optical fiber, but the underlying mission remained astonishingly consistent. Make the world feel closer by crossing water. That is why the modern system should be understood not as a novelty, but as the latest layer in a long historical stack. The cables on the seabed today are the descendants of the first experimental lines that asked whether an ocean could be threaded with communication. Each generation made the next possible. Each success reduced the shock of distance a little more. What began as a daring answer to a 19th century problem has become the planet-scale broadband system that modern life depends on. And that is the deeper story hidden inside the cable map. The internet did not appear all at once, fully formed and weightless. It was built by repeating a very old engineering promise. If the gap is too wide, bridge it. If the bridge fails, make it stronger. If the world grows more connected, widen the bridge again. The ocean floor still carries that promise. In the next layer of the story, the question is no longer just how people learn to cross the abyss, but how a single cable can carry so much of a continent's life once it gets there. The strange thing about the internet is that it feels weightless right up until the moment you follow it far enough. Then the illusion breaks. What looks like a cloud turns out to be a machine, a long, engineered chain of glass, steel, and power that begins on the seabed, rises to shore, and keeps going inland long after the ocean ends. In industry terms, the part in the water is the wet plant, and that wet plant is the core of the whole system. It is where the cable itself and the repeaters do the hard work of carrying data across an entire ocean. At the center of that machine is a fiber-optic cable built for a world that is trying to crush, corrode, and disturb it. The inner fibers carry light. The outer protective layers are there to survive deep-sea pressure, corrosion, and the constant risk of marine activity. The point is not just to make a wire that can go underwater. The point is to make a communications line that can remain physically intact for years in an environment that is hostile to almost everything else humans build. But even the cleanest glass fiber cannot carry a signal endlessly. Over long distances, the light fades. That is why submarine systems rely on repeaters, underwater pressure vessels that contain optical amplifiers for the fibers running through them. In modern systems, those amplifiers are typically erbium-doped fiber amplifiers, and they are placed at intervals designed to preserve signal quality across the route, often around every 70 to 100 kilometers. They do not rebuild the message from scratch. They simply boost the light so it can keep going. This is where submarine networking departs from the familiar logic of land fiber. On land, cables are often added to a pre-existing web of rights-of-way, ducts, and routes. Under the sea, the system starts with a clean slate. Engineers choose the transmission path, the fiber type, and the spacing of amplifiers for that specific route, because every ocean crossing is its own design problem. The cable is not just extended from shore into the water. It is designed as an end-to-end system, span by span, with capacity and reliability balanced against distance and power. That power matters because submarine repeaters are fed from land. High-voltage electrical power is sent through the cable itself from terminal stations on shore, with the current running out along the submerged line to keep the amplifiers alive. Science Direct describes voltages as high as 15 kilovolts and line currents in the hundreds of milliamps, a reminder that this supposedly invisible network depends on a very physical supply chain. The data may be light, but the system is held together by electricity, metal conductors, and careful engineering over thousands of kilometers. When the cable finally reaches land, it does not simply plug into the internet. It passes through a beach manhole and into the cable landing station, the place where sea traffic becomes terrestrial traffic. That station houses the power feed equipment that energizes the wet plant and the submarine line terminal equipment that converts submarine signals into signals the land network can use. From there, traffic enters backhaul networks, often through facilities farther inland, so the real end of the cable may be miles from the shore. A landing station is not a footnote to the cable. It is the hinge between ocean infrastructure and the rest of the digital world. Seen this way, a cable's capacity is not measured only by how many fiber pairs lie inside it. It also depends on route length, amplifier spacing, optical power, terminal equipment, and the infrastructure waiting for it at the coast. The design capacity is a system property, not a single specification. A shorter route can tolerate different spacing than a longer one. A stronger amplifier chain can preserve more usable signal. A better landing and backhaul network can move more traffic into the continent. The cable is elegant because so many things have to work together. It is fragile for exactly the same reason. And that is the hidden lesson of the undersea network. The ocean floor does not connect the world by accident, or by magic, or even by fiber alone. It connects the world through places, through power, through carefully chosen landfalls and inland handoffs. Once you understand the machine beneath the waves, the next question becomes unavoidable. Why are some coasts crowded with cables while others sit far from the main routes? The answer lies not just in engineering, but in geography. A cable does not land everywhere. It lands where the world has decided it is worth landing. At the edge of a market, beside a port, near a major city, on a coast where the water is deep enough, the seabed is workable, and the business case can survive the cost of building across an ocean. That is the first lesson the map teaches. The internet may feel like a universal cloud, but its physical form is stubbornly selective. It gathers in corridors, thins out at the margins, and knots itself around a relatively small number of shorelines and stations. Telegeography's latest global map makes that concentration impossible to miss. The world's submarine system is not a single seamless net draped across the oceans. It is a sprawling collection of hundreds of active and planned systems, tied together by nearly 1,900 landing stations. In other words, the internet does not touch every coastline equally. It arrives in chosen places, through specific gates, and then disappears inland along terrestrial networks that are just as important as the cable in the sea. The ocean floor may carry the long-haul traffic, but the geography of connection is decided at the shore. Look at the great routes, and the pattern becomes even clearer. Some of the busiest arteries follow the lines of global trade and global finance. The North Atlantic remains one of the most important corridors because it links major markets with extraordinary density between North America and Europe. Across the Pacific, another huge concentration of systems connects the United States and East Asia, carrying the demands of cloud platforms, content delivery, manufacturing supply chains, and financial activity across the world's largest ocean. Between Europe and Asia, many routes converge through the Red Sea and Egypt, where geography narrows the passage between seas and turns a regional crossing into a global bottleneck. Around Asia itself, dense intra-Asian links stitch together places like Japan, Singapore, Hong Kong, South Korea, and Southeast Asia, reflecting how much of modern digital commerce happens not just between continents, but within a single fast-moving economic region. These routes do not exist because engineers drew elegant lines on a map. They exist because demand clusters in particular places. A cable is a staggering investment before it is ever useful. It must justify itself in traffic, in latency, in contracts, in the promise that enough data will move across it to make the business viable. That is why cables tend to follow economic gravity. They go where the largest populations, the busiest exchanges, the biggest cloud hubs, and the richest communications markets already are. The ocean is open, but capital is not. And so the network forms around the places where the returns are most likely to be captured. That is why the map is also a map of inequality. Some regions sit at the center of many routes, with multiple landings and dense redundancy, while others are served by only a few systems, often along a narrow set of coastal approaches. The difference is not just technical. It is historical, commercial, and political. Places that sit inside the world's major trade lanes tend to attract more routes because they are easier to monetize. Places that are politically unstable, geographically isolated, or economically less central often receive fewer. The result is a global communications system that is connected, but not evenly connected. The internet reaches far, but it does not arrive everywhere with the same abundance. Landing stations reveal this concentration even more sharply than the map of cables themselves. A landing station is not a picturesque seaside waypoint. It is a secured infrastructure site where multiple submarine systems can converge, each one carrying traffic that may fan outward to entire regions. A single coast can host several cables, and several cables can terminate in the same general area, which means that the loss or disruption of a landing point can ripple far beyond the shoreline. The station becomes a hinge between the sea and the land, and like any hinge, it can matter out of all proportion to its size. This is why the geography of landing is so important. A cable that appears to be one route on the map may in practice depend on a small cluster of terrestrial corridors, power feeds, switching sites, and backhaul lines once it reaches shore. If those inland paths are narrow, the whole system is less resilient than the ocean distance might suggest. The traffic may be able to reroute, and often it does, but rerouting depends on whether there is spare capacity elsewhere and whether the surrounding network has enough diversity to absorb the shock. In one region, a fault can be little more than an inconvenience. In another, the same kind of event can slow traffic, raise latency, and expose the fragility of a route that seemed dependable on paper. This is the part of the story that is easy to miss if you stare only at the blue lines of a cable map. The true shape of the network is not only the path across the seabed, it is the concentration of landings, the clustering of systems near major cities, the narrowness of certain passages, and the fact that the Internet's most important connections are built around a handful of strategic geographies. The world's digital system is not spread evenly over the planet like weather. It is built like commerce itself, clustered, selective, and pulled toward places that already matter. And because it is built this way, it inherits the logic of every other infrastructure system that concentrates value in a small number of nodes. The more traffic depends on a route, the more valuable that route becomes. The more valuable it becomes, the more attention it attracts. A coastline with several landings is not just a technical asset. It is a point of leverage. A corridor that carries a huge share of international communications is not just a feat of engineering. It is a fact of global organization. The same geography that makes a route efficient can also make it sensitive. That sensitivity is what sits just beneath the surface of the map. When so much of the world's data, trade, finance, and cloud traffic flows through a limited set of undersea paths and landing points, infrastructure ceases to be merely infrastructure. It becomes a question of control, resilience, and power. The ocean floor is no longer just where cables happen to lie. It is where the architecture of the modern world can be sped up, rerouted, strained, or threatened. And once that becomes clear, the next question is not simply where the cables go. It is who relies on them, who protects them, and who notices when the lines that feel invisible suddenly become impossible to ignore. For most people, the Internet still feels like a force without a body. It arrives as a tap, a swipe, a click. It seems to belong to the air around us, to satellites, to towers, to the invisible cloud. But beneath that illusion is a hard and stubborn reality. The global Internet depends overwhelmingly on fiber-optic cables laid across the seafloor. And once you understand that, the ocean stops being empty space. It becomes a strategic corridor. That shift matters because these cables are not carrying some niche stream of background data. They carry the traffic that modern societies run on: financial transactions, cloud services, government communications, digital health records, education systems, business operations, and the everyday exchange of information between countries. In other words, they do not merely connect people to entertainment or social media. They connect states to states, markets to markets, and institutions to the systems they increasingly depend on. This is why submarine cables have moved so far beyond the domain of engineers and telecom specialists. They are now part of how power is exercised. A route across the seabed can be a commercial decision, a diplomatic decision, or a security decision. Who owns the cable, who finances it, who can land it on shore, and who controls the traffic once it reaches land can matter as much as the length of the route itself. The physical line under the sea may be the same thin strand of glass and steel, but the leverage wrapped around it can be very different. That is part of what makes submarine infrastructure so politically sensitive. A cable is not just a line connecting 2 points on a map. It is a legal regime, a landing permission, a set of corporate interests, a terrestrial backhaul network, and a chain of dependencies stretching inland from the shore. The cable comes ashore at a landing station, and from there the data still has to move through terrestrial networks to reach cities, offices, data centers, and government buildings. The ocean floor may carry the international link, but the landing point determines how that link enters a country and who can influence what happens next. Governments understand this. They have to. If the cables fail, the effects are rarely total, but they can be serious and uneven, especially in places with fewer alternative routes. Traffic can sometimes be rerouted, and the internet is often more resilient than it looks. But resilience is not the same thing as indifference. When capacity is concentrated, when landing stations are clustered, or when a region depends on a narrow set of routes, disruption can raise costs, slow services, and expose vulnerabilities that are otherwise hidden. A cut cable may not silence a nation, but it can shake the systems that nation relies on. That is why international concern has grown around these cables as strategic assets. In 2024, the International Telecommunication Union and the International Cable Protection Committee created an advisory body focused on submarine cable resilience, bringing attention to deployment practices, maintenance, repair, redundancy, and best practice coordination. The very existence of such a body is a reminder that this is no longer a sleepy corner of telecom infrastructure. It is an area where engineering, law, and security now overlap. And the reason is simple. The world has become too dependent on the lines under the sea to treat them as invisible forever. The more digital the economy becomes, the more these cables resemble critical public utilities, even when they are privately owned or jointly financed. Their value is not only in the data they carry today, but in the continuity they promise tomorrow. That promise is what companies sell, what governments rely on, and what markets assume will still hold even when no one is looking. Yet the question of control is not just about whether a cable exists. It is also about where it exists and who can reach it. Some coasts are crowded with cables and landing stations. Others are sparsely connected. Some routes pass through choke points where geography funnels multiple systems into the same narrow space. In those places, strategic advantage and strategic risk sit side by side. The same concentration that makes a route efficient can also make it consequential. If a few nodes carry a disproportionate share of a region's international traffic, then a company, a country, or even a local community can find that its digital life depends on infrastructure it does not directly see and may not control. That is one reason submarine cables have become objects of state interest. They are owned by consortia, telecom operators, tech companies, and sometimes governments. They are negotiated over, licensed, protected, repaired, insured, and watched. They carry commercial advantage, but they also intersect with sovereignty. A country may welcome a new route for its economic benefits and worry about it for its security implications. It may need foreign capital to build it and foreign cooperation to keep it reliable. It may depend on a cable system that links it more closely to the world, while also making it more exposed to the world's tensions. The geopolitical importance of undersea cables also comes from a more uncomfortable fact. They are common enough to fail. Faults happen every year, and enough of them happen that they can no longer be dismissed as rare anomalies. Repairs are not theoretical either. They are routine enough to require an international industry of specialized ships, crews, planning, and coordination. That reality has changed how states think about these systems. The issue is no longer whether a submarine cable might need attention. It is how quickly attention can be mobilized, how many alternatives exist, and who bears the consequences when something goes wrong. So the ocean floor becomes something more than a technical map. It becomes a place where commerce, law, and security collide. It becomes a place where private investment intersects with public dependence. It becomes a place where a cable laid for speed can also become a subject of surveillance, competition, and contingency planning. The seabed is not just infrastructure in the ordinary sense. It is infrastructure that carries the weight of modern sovereignty. And that is the deeper reason these cables matter now. They are not simply pipes for bits. They are the hidden architecture of a connected world, and every nation that depends on that world has a stake in who builds the lines, who owns them, who maintains them, and who is prepared when the system is tested. The question is no longer whether the internet is wireless. It is whether the physical network beneath the water can keep its promise of continuity when pressure rises, traffic surges, and the line between commercial transport and strategic asset begins to blur. Because once a system becomes that central, even the smallest interruption is no longer just a technical event. It is a warning. The strange thing about the internet is that it is designed to make interruption feel impossible. Messages arrive before we notice the distance they traveled. A payment clears, a video loads, a call connects, and the machinery behind it is supposed to disappear. But beneath that illusion of continuity is a system that lives with failure all the time. It is built for it, planned around it, measured against it, because the ocean floor is not a pristine, untouchable corridor. It is a working environment, crowded with anchors, nets, currents, pressure, shifting seabeds, and time. Every year, submarine cable operators deal with faults in the hundreds worldwide. Some are small, some are serious, and some are repaired before most people ever know anything happened. In 2023 alone, there were more than 200 repairs reported. That number matters less as a sign of fragility than as a sign of how much work goes into preserving the illusion that the network is seamless. Continuity on the internet is not an accident. It is the outcome of constant maintenance. Most cable failures are not dramatic acts of sabotage. They are ordinary, almost industrial in their causes. Fishing gear drags where it should not. Ships anchor where charts and caution say they should not. Undersea slopes shift. Seabeds move. Equipment ages. A cable that has spent years under stress can still be broken by the cumulative weight of the world above it. The sea is vast, but the places where modern communications touch it are narrow and vulnerable, especially near shore, where traffic, weather, and human activity are all concentrated. And yet the system is not brittle in the way a single broken line would be brittle. It is resilient because it is redundant. Traffic can be rerouted, capacity can be shifted. Other cables can absorb the load, at least for a time. That is why a cut does not automatically become a global outage. The internet is not one pipe. It is a web of pipes with alternate paths, competing routes, and varying degrees of spare capacity. When one line fails, the system often bends instead of breaking. But bending is not the same as escaping impact. Redundancy is uneven. Some regions have many routes and many landing points. Others depend on a smaller number of choke points, where the loss of one cable can strain the rest. If routes are concentrated, if spare capacity is limited, if several systems share the same corridor or the same coast, the consequence of a fault can spread much farther than the break itself. What looks like a local problem in deep water can become a regional problem on land, affecting businesses, cloud services, financial flows, and everyday connections that depend on a very particular path under the sea. That is why the repair industry exists as its own hidden world. When a fault is suspected, engineers first have to locate it, narrowing the problem down across an immense distance of cable. Then a specialist vessel is dispatched. These are not ordinary ships. They are floating workshops built for precision work in difficult conditions, carrying the equipment needed to retrieve a cable from the seabed, bring it to the surface, and restore the broken section. The damaged span is lifted carefully, cut back, and spliced to healthy line. Then it is lowered again, returned to the seabed, and tested until service can be restored. It is slow, technical work. Weather can delay it. Distance can delay it. The availability of repair ships can delay it. Even when everything goes well, the process reminds you that the network we use every second depends on a chain of physical labor that most people will never see. The internet may feel instantaneous, but its repair is anything but. It is an offshore emergency response system, stretched across the planet. That is why resilience is the right word, but only if it is understood correctly. Resilience does not mean nothing goes wrong. It means the system has been designed with the expectation that something will. It means operators build alternate routes, plan for congestion, and maintain spare capacity not because failure is rare, but because failure is part of the operating environment. The whole arrangement depends on keeping interruptions from becoming catastrophes. And that, in the end, is the deeper truth of undersea cables. They are not magical conduits suspended beyond risk. They are engineered, inspected, repaired, rerouted, and watched over by a global industry whose job is to keep the world connected despite everything that tries to pull it apart. Their strength is not that they never break. Their strength is that when they do, the system around them is supposed to absorb the shock. But that promise only works if the network keeps growing, if redundancy keeps pace with demand, and if the people who depend on these cables keep treating them as essential infrastructure rather than invisible background. Because the pressure on the system is not going away. More data moves every year. More services depend on it. More governments are paying attention. More routes are being planned, and more resilience work is being demanded. So even here, in the chapter of breakdowns and repairs, the story does not end with interruption. It points forward. The question is not whether the line will ever break. It will. The question is what kind of network we build, knowing that it will, and whether the next generation of cables can carry not only our data, but our growing dependence on the quiet world beneath the sea. From the surface, the internet can look immaterial, as if it were made of air and signals and the invisible glow of screens. But the system underneath keeps getting larger, not smaller. ITU says the total length of submarine cables worldwide has grown by more than 70% over the past decade, and that the global network now includes more than 500 active and planned cable systems, stretching beyond 1.7 million kilometers. This is not a finished inheritance from the early internet. It is an expanding industrial network, laid one route at a time because the world keeps demanding more capacity, more reach, and more resilience. The map also tells a more precise story about where this network really lives. Telegeography's 2026 map counts 1,893 landing stations, which makes clear that submarine cables do not disappear neatly into a universal shoreline. They converge at specific coastal gateways where the line at sea becomes equipment on land, and then terrestrial backhaul that carries traffic onward inland. The cable itself, the landing station, and the onshore network are distinct parts of the same system. And that distinction matters because the internet's physical geography is concentrated, not evenly spread across every coast. That concentration is why resilience has become the next phase of the story. In 2024, ITU and the ICPC created the International Advisory Body for Submarine Cable Resilience to promote better maintenance, faster recovery, stronger redundancy, and closer coordination between governments, operators, and maritime authorities. The point is not to deny that faults happen. It is to accept that they will happen, and then build a network, a policy framework, and a repair system that can absorb the interruption without letting it become catastrophe. In other words, the future of submarine infrastructure is not just about laying more cable. It is about making the whole system smarter about how it breaks and how it heals. And the build-out is still moving. ITU continues to describe submarine cables as the backbone of global communications, carrying roughly 99% of international data exchanges, while telegeography says 2026 is shaping up as another strong year for the industry, with nearly 40 cables projected to enter service after roughly 15 in 2025. That growth follows a simple logic. Every new cloud region, every cross-border payment, every remote backup, every video call, every government transaction that depends on instant international exchange creates another reason to add route diversity and capacity beneath the sea. The future internet is not less physical than the one we have now. It is more so. Some of that future may also be multifunctional. ITU's smart cable work imagines submarine systems that still do the basic telecom job, but also carry sensors for ocean temperature, pressure, and seismic motion. In that model, a cable can become part communications backbone and part environmental instrument, helping with climate monitoring, earthquake detection, and tsunami warning. It is a striking reversal of what people usually expect from infrastructure. The same line that moves business data and state communications could also collect public scientific data from the deep ocean. The cable would still be ordinary engineering, but it would be doing more for the public than most people ever notice. That is the final irony of the Internet's hidden geography. Its most magical feature is speed, but its future depends on patience. Survey ships, permits, landing sites, protected corridors, repair planning, standards, and international agreements. The thing that feels least physical in daily life is becoming more dependent on physical discipline, not less. So the next internet will still be underwater, stretched across the seabed in quiet lines of glass and armor, carrying our data as it has for generations, and perhaps carrying something more as well. The recognition that the modern world runs on ordinary engineering placed carefully in the dark.